Hello and welcome to this video on rotational motion. Specifically today we're going to be talking about torque. What is it? How do we calculate it? How do we find it? Thus far in this unit we've been taking linear motion equations and plugging in rotational terms using the relations that we have here. The distance something goes is equal to theta times the radius. Its tangential velocity is equal to omega times the radius. And its tangential acceleration is equal to alpha. It's angular acceleration times the radius. We've done it with kinematics, getting our rotational motion equations. We've done it with energy, getting our rotational energy equations. Today we're going to do it with force. Previously we talked about how the net force acting on an object is equal to its mass times acceleration. So if I have a point here with a mass, and apply a force to it, I'll get an acceleration. Now, to start, we're only going to talk about one force. So, in this case, whatever force this might be, if it's the only force acting, equal mass times acceleration. When we translate this, when we move this into talking about rotational reference frames, we replace the A with alpha r. Now, this has to be a perpendicular acceleration. Why is that relevant? We'll get to in a little bit, but the fact that it does have to be a perpendicular acceleration tells us something going down the road. So I replace the A with the alpha r, and I get something that's not particularly useful. This doesn't tell me anything, it doesn't look like anything we've done. If I cheat, however, and multiply both sides by r, and then do a quick rearrange, I get r times F equals mr squared alpha. And mr squared is the moment of inertia for a single point. If I start adding all my forces together, if I start adding all the different forces, going back to multiple forces, this becomes the moment of inertia. And the sum of all my forces acting at a radius is what we define as torque. In short, the net torque using tau acting on a system is equal to the sum of all the r times f's moment of inertia times alpha. And much like how the net force was equal to mass times acceleration, the net torque is equal to I times alpha. But as I said previously, this is a tangential acceleration. It is acting directly perpendicular to. Why does that matter? Well, imagine a wheel, if you will. If I have a wheel outlined in red and I apply a force right here at the top, I'm going to get a lot of acceleration, a large alpha. If I push here in the middle and I still push directly out to the right here, I'm going to get a smaller alpha. And if I go to the edge of the rim and pull directly out, not in the direction it wants to rotate, just straight out, I don't get an alpha at all. When we talked about work, we talked about how we only cared about the force in the direction of travel. In this case, we only care about the force perpendicular to the radius. In this case, this here gives me no torque because the force and the radius are in the same direction. Here, I get a lot of torque, a lot of angular acceleration because they're perpendicular. And if I go for this middle point here, only some of it is perpendicular to how much? Well, we're looking for the amount perpendicular. If I were to draw a triangle here using my vectors, with this force here being here, and this force being here, and my vector for radius being this way, the amount that's perpendicular is on this side. It is the sine. In calculus, we refer to this as the cross product. That's calculus, and this is an algebra-based class. So instead, we refer to the r perpendicular to the force, or we use the shorthand rf sine theta. Of course, the angle here is the angle between the direction of rotation and the force. For instance, if I look at a wrench, pushing. The point of rotation is here in the center. Rotate around this point. The radius, it goes from the center to where the force is being applied, here by the hand. And the force in this case would be pushing downward. Now, in an ideal perfect situation, you're pushing directly perpendicular. But in this case, the angle here is slightly larger than 90 degrees. So I wouldn't get the full torque out of the force I'm exerting. Torque, much like an angular acceleration and an angular velocity, has a positive and negative direction. In this case, the torque is going to cause this to move counterclockwise. It's going to cause it to move this way. So the torque in this case is positive. Positive torque causes counterclockwise acceleration. Understanding and visualizing how this works becomes difficult for some people. So in many cases, we revert to what's known as the right hand rule. Taking your right hand and putting your pointer finger and middle finger at a right angle, like is depicted here, and then sticking your thumb up will tell you the direction of the torque. If the torque is pointing out of the page, you have positive torque. Into page, you have negative torque. This seems a little confusing, but let's break it down. So here we have two kids on a seesaw. This point here, this blue dot, is your center of rotation. It's where the seesaw pivots around. If I draw a line from here to the first child, like so, that's my radius. Gravity, in this case, is going to try to pull the child down. If I take my pointer finger and put it along the R, the radius, and then I put my middle finger down along the force gravity and align it up, I'll notice that my thumb is pointing into the screen. Give it a try right now. Do it yourself. See how that thumb points in. This is going to be a negative torque. It's going to cause a clockwise acceleration. On the other side, this child, R points this way. And then the force of gravity, the weight of this child, points down. If I do the same process here, I get positive torque because my thumb points out of the screen. And this is going to give me counterclockwise acceleration. But what about the middle? What about the pivot point? What about the normal force exerted here? Well, there is no radius. There's no distance between the pivot and the normal force in this case, but the normal force does point up. However, the normal force in this case has no radius. It'll exert no torque on the system because it is at the center of rotation, at my pivot point. Now, actually calculating these torques will depend on the angle in each of these cases, but regardless of what the angle is here, or here, or here, these angles, we can see using the right hand rule whether the torque will be positive, negative. What if we wanted to actually calculate the torque in each of these cases? To make it easy on ourselves to start, let's imagine this is level. So each of these angles here are 90 degrees. They're not in the image. For the sake of ease of calculation, we're going to use them as 90 right now. Talk about it. This child here is a distance of 1.8 meters from the center and has a mass of 70 kilograms. This one is a distance of 2 meters and has a mass of 65 kilograms. To find the total torque of the system, to find the net torque, which will equal the moment of inertia times alpha, all I need to do is find all the individual torques. So the torque from the normal force plus the torque of the blue plus the torque of the green will add up to give me my total torque. And in each case, all I need to do are perpendicular times F. Go ahead, give it a try. Check back after the pause. Okay, let's go through this really quick. The first thing I did was just write down all the forces and the radiuses. So R0 times Fn plus negative. I know it's negative because of the right-hand rule. This person's going to try to cause the seesaw to accelerate in a clockwise direction, at least from our point of view. 1.8 times the mass times g, 70 times 9.8, plus positive, this person is going to cause it to accelerate counterclockwise, 2.0 times 6.5 times 9.8. Put it on my calculator, I get 39.2 newtons times meters. R is in meters, F is in newtons, newtons times meters. This is the unit of torque. It's analogous to a foot-pound, which you typically hear when you're talking about race cars and their torque and how fast they can go. One of the big tricks here, actually, though, is I didn't know my normal force. I didn't have a good way to find it. And normal force typically can only be found in reference to other forces. It's how we did it in the dynamics units, how we're going to do it here. But because I didn't know my normal force, I typically would have been able to solve this problem. But here, by choosing my axis of rotation, by choosing to say I'm rotating around this point here in the center, I made the radius to my normal force 0, which meant I didn't need to care about it. A common trick when solving torque problems is to take whatever force you don't know, doesn't matter where it is, and choose that to be the point you measure your radius from. This is the greatest piece of advice I ever got about solving a torque problem. If you don't know a force, make it to be your point of rotation, choose it to be your center. Then you won't need to care about it. Don't know, don't care.